you handle cash sometimes, right? Maybe grabbing coffee, paying back a friend. It's so routine, you probably don't think twice about it. But there's this kind of hidden problem lurking in those transactions. Counterfeit currency.
And it's a much bigger deal than just, getting stuck with a fake note. Counterfeiting, it really strikes at the heart of economic stability. It fuels financial crime. And maybe most importantly, it eats away at that fundamental trust we all need to have in money itself.
Right. And here's where it gets really interesting for me. Spotting a good counterfeit, telling it apart from a genuine banknote, well, it can be incredibly difficult for a human eye, especially when they're designed to be almost identical. Those little security features. So easy to miss if you're busy or the light's bad or, you're just not trained to look.
Exactly. Relying solely on manual inspection just has clear limitations. It's slow. It can be inconsistent. So our deep dive today is looking into how artificial intelligence is being developed to tackle this exact real-world challenge. We're digging into a specific research article that explores using a pretty powerful AI technique called Yolov8
Right, Yolov8.
to automate the detection of counterfeit Nepali banknotes.
Okay, let's unpack this then. The goal, the mission, as this research sort of lays it out, is to build these automated systems that are, one, highly accurate, two, super efficient compared to human checks, and ideally flexible enough, right? So they could work not just with Nepali currency, but maybe be adapted for currencies worldwide, maybe on different devices too.
Precisely. And what's fascinating here is the specific test case they chose. This research really zeroes in on the 1,000 Nepalese rupee banknote, and it's a note that's actually packed with different security features, all designed to make counterfeiting harder and hopefully detection easier.
For those who know what to look for anyway. And the paper, it details these features. Some are purely visual, right? Others need like touch or specific light conditions. You've got the watermark, for instance, hold it to the light, and you're supposed to see the shape of the Laligra's flower appear.
Right. And then there's the see-through register, hold it up again, and the number 1,000 should line up perfectly front to back. There's also that security thread, the little strip embedded in the paper. If you tilt the note, it reveals the letters NRB and 1,000.
Then you've got the features you actually have to feel, the raised inks, which give a sort of distinct texture to certain parts of the note.
Yes, and there's a specific Braille feature too,
Yeah.
little raised M, which helps visually impaired individuals identify the denomination just by touch, and also an emboss feature, another raised area that can sometimes even show a kind of metallic silver effect when you tilt it.
And finally, they mentioned the iridescent effect, right? Visible in certain patches when you tilt the note, just so. So you've got this whole multi-sensory challenge, looking, feeling, tilting, holding it up to the light. It's quite a sophisticated set of defenses they've built in.
It really is. And that complexity highlights the challenge, doesn't it? Yeah. Manually checking all of these features consistently every single time, doing it accurately and quickly, well, it's incredibly difficult in practice.
Yeah, I can see that.
And this is exactly where the promise of automation using AI really comes into play.
So how does the AI actually approach this? The article points to these automated algorithms leveraging AI as a really promising way forward to improve both the accuracy and the speed over manual checks.
And they specifically turn to a type of AI known for its speed and accuracy in like finding objects within images. It's called YOLO. Stands for you only look once. It's gone through a lot of evolution, and V8 is one of the latest iterations. It's known for being pretty fast and quite versatile.
Okay, Yolov8. And they used a specific version, the nano model, and focused on something called segmentation-based classification. Why segmentation? How does that help with spotting fake money?
That's a really good question. So instead of just having the AI look at the whole banknote image and make a single judgment like fake or real, segmentation is more like telling the AI to break the image down into tiny pieces or regions first. It then analyzes each specific region based on its characteristics, things like color, texture, patterns, shapes within that little area.
Okay. So it's not just looking for a general fakeness vibe. It's actually zeroing in on specific areas where, say, a security feature should be, or where fake notes might show really subtle flaws, like pixel by pixel almost.
Exactly that. By segmenting the image, the AI can focus its analysis really precisely on those locations where security features exist. This makes it much better, potentially, at spotting those tiny discrepancies or imperfections in counterfeit attempts right within those specific zones. It's analyzing the parts, not just judging the whole picture.
Okay, that makes sense. So how did they actually test this out? Walk us through the research process they described.
Well, they started with the data, obviously. That's always crucial for any AI project. They gathered images of both genuine and counterfeit 1000 NR's notes. They had 180 samples of each. And importantly, the authenticity, whether they were real or fake, was verified by the government of Nepal.
Right, so they knew for sure what was what, and they used mobile phones to take the pictures.
Yeah, aiming for a kind of realistic scenario, capturing images like you might in a real-world setting.
And then before feeding these images to the AI, they had to clean them up, I guess. Remove the background clutter.
Yes, exactly. They developed an automated process to crop out the background, basically isolating just the banknote itself. This involved steps like converting the images to grayscale first, and then using something called template matching to find the note's edges and cut away everything else.
Makes sense. You want the AI focused just on the note, not distracted by, like, the table it's sitting on?
Precisely. And for the heavy lifting, the actual training of the AI model, they use Google Colab, which gives access to powerful GPUs, in this case a T4 GPU. You need that kind of processing power.
Great. Did they mention trying other AI models before settling on Yolov8?
They did, briefly.
Yeah.
They mentioned exploring models like MobileNet V2 and ResNet V2 earlier on. But they apparently ran into some common issues, like overfitting. That's where the model learns the training data too perfectly, almost memorizes it, but then fails when it sees new, slightly different images. It doesn't generalize well.
Ah, okay. So that pointed them towards needing a more robust approach, which led them to Yolov8.
Seems that way. So then they prepared the data specifically for Yolov8. This involved annotating the images.
Which means what exactly?
Basically, drawing boxes or creating masks around the areas of interest on each image. So highlighting where the key security features are or marking known flaws on the fake notes. They use tools like the VGG annotation tool for this.
Got it. Labeling the important bits.
Yeah. And they also applied various image augmentations during training. Things like slightly translating the image, scaling it, shearing it basically, artificially creating more variety in the training data.
Why do that?
Well, it helps the AI learn to recognize the features, even if the banknote in the image isn't perfectly centered or perfectly flat or taken under absolutely ideal lighting. It makes the model more robust to real-world variations.
Okay, right. Builds resilience. So let's get to the results then. How well did this Yolov8 model actually perform? They used standard metrics, didn't they? Precision, recall.
They did. The key metrics they reported were mean average precision, or MEP, average precision, EP, precision itself, and recall. Just to quickly break those down. Precision basically tells you, out of all the notes the AI flagged as fake, how many were actually fake. High precision means fewer false alarms.
Okay. And recall.
Recall tells you, out of all the actual fake notes that were in the dataset, how many did the AI successfully find or identify. High recall means it doesn't miss many fakes.
Got it. Fewer false alarms with precision, fewer missed fakes with recall. So how did Yolov8 do on those?
Pretty strong results, actually. It achieved a true positive recall of around 82.5% for the front face of the note. And interestingly, a much higher recall, nearly 98.6% for the back face. The study reported significant overall improvements in accuracy metrics like MAP compared to their earlier tests with other models.
And they didn't just test Yolov8 in isolation, did they? They compared it directly with an earlier version, Yolov5.
Yes, exactly. They trained a Yolov5 model in the very same data, same setup, to do a head-to-head comparison.
How did they stack up?
Yolov8 came out on top. It consistently outperformed Yolov5 in the MAP scores across different confidence thresholds they measured, and for both the front and the back of the note. So this really seemed to validate their choice of using Yolov8 and particularly the segmentation-based approach for this kind of task.
But, okay, here's where it got really interesting for me, and maybe shows a kind of nuance in how these AI models work. They did a specific statistical test, didn't they? A chi-square test.
They did, yes, on a specific, smaller subset of the images. They took 20 images that, between them, contained 51 distinct, known fake regions.
So a targeted test on areas they knew were counterfeit.
Right, and that test revealed a statistically significant difference between how Yolov5 and Yolov8 performed on that specific sample. They reported a p-value, which is a measure of statistical significance, that was incredibly small, like 7.29 times 10 to the minus 8. Basically, it means the difference they saw was overwhelmingly unlikely to be just random chance.
Okay, so a real difference. What was the difference on that specific sample of 51 fake regions?
Well, this is the fascinating part, and it highlights that trade-off we sometimes see. On that particular set of 20 images with 51 known fake bits, Yolov5 actually detected all 51 regions. It flagged every single area that contained a known counterfeit feature.
Wow. Okay, 100% detection on that sample. That sounds amazing, doesn't it?
Well, it sounds great for detection, yes. find all the problems. But the study points out that Yolov8 lacked precision on this sample. It seems it might have been flagging broadly, maybe catching the fakes, but perhaps also flagging areas that weren't definitively fake, or not pinpointing the exact flaw precisely.
Okay, so it found everything, but maybe wasn't very specific.
That seems to be the implication. In contrast, Yolov8, on that very same sample, didn't flag all 51 regions. It predicted, I think the number was 21 regions as fake and 20 as not fake within that sample set. And the study's conclusion from this test was that Yolov8 demonstrated superior precision. It was better at correctly identifying only the actual fake portions within those regions it flagged.
Okay, right. So that statistical test really highlighted a trade-off. YOLO5 on that sample acted maybe like a wide net. It caught all the target fish, the fake regions, but maybe also scooped up some other stuff, non-fake areas, or just flagged the whole area vaguely. Whereas YOLO8 was more like a spearfisher. It didn't catch absolutely everything, but what it did catch, it identified with much higher confidence and precision, hitting just the actual fake feature.
That's a pretty good analogy, yeah.
Yeah.
And depending on what you need the system for, that level of precision, knowing exactly what's wrong and where, could be incredibly valuable. Maybe even more valuable than just getting a general warning about a suspicious area.
Very interesting distinction. Now, we should also talk about the limitations, right? The researchers themselves were careful to point these out.
Absolutely, and it's crucial for context. A major limitation, they state, is that the model was trained to detect only 8 specific security features that they identified and annotated. Real counterfeit notes might have other kinds of flaws or use different techniques that this AI simply wasn't trained to look for. You would miss those entirely.
And maybe a more fundamental limitation. This whole method is purely image-based. It relies on what a camera sees visually. So it fundamentally cannot detect security features that depend on touch or texture. Things like the raised inks, the braille feature, that emboss feature, you have to feel those. The AI has no sense of touch.
Correct. And it also can't really verify features that require specific conditions not usually captured in a standard static image. Think about the iridescent ink that changes appearance when you tilt it in the light, or that see-through register which only works properly when you hold the note up to a light source. An image taken flat on a table just won't capture that information.
Yeah. So while it's clearly powerful for analyzing the visual details it can see, this AI kind of hits a wall when it comes to security features designed specifically for other human senses or those requiring dynamic interaction like tilting or backlighting.
That's a key takeaway, definitely. Despite how advanced this AI is, current image-based systems are still limited by the type of input they receive the visual data. So the overall conclusion from the research is that using image segmentation, particularly with this Yolov8 model, provides a highly effective framework. It's good at detecting counterfeit currency by focusing intensely on those subtle visual details.
And the strong performance numbers they got, especially with Yolov8 compared to V5, certainly show its potential for, real-world use in financial systems, maybe in sorting machines or verification apps.
They do note, though, that while the core methodology seems solid, its actual performance out in the wild will always be influenced by factors like image quality, different lighting conditions, variations in note designs over time, and, of course, the constant innovation by counterfeiters, who are always trying to find new ways to bypass security measures. It's like a technological arms race, really.
Always evolving. And their stated future work, what they want to do next.
Well, they mentioned wanting to continue fine-tuning the model, making it even better, and, importantly, expanding its application beyond just Nepali currency. The goal is to see if this framework can be adapted to tackle counterfeit detection for currencies globally. That broader applicability is key.
Fascinating stuff, seeing how this cutting-edge AI is being applied so directly to protect something we all handle pretty much every day.
It really is.
So what does all this mean for you, our listener? Well, it means that the technology working behind the scenes to protect your money is getting incredibly sophisticated. Automated systems like the one we've been discussing from this study are becoming vital tools in the fight against financial fraud and, critically, in maintaining that trust we need in our currency.
And the statistical test we talked about, the Yolov8 versus V8 comparison, it highlights a really important point about AI itself, that how a model is designed, like using segmentation here, and what metrics you prioritize, like precision versus just broad detection, well, those choices fundamentally shape its performance and really determine where its strengths lie you apply it to a complex real-world problem like this.
Okay, so bearing all that in mind, and remembering that even this advanced image-based AI system still has limitations, right? It can't feel the raised ink, it can't hold the note up to the light in the same way a person can. Here's a thought for you to consider. Does the human element with our multiple senses and ability to interact with the note, does that remain an essential, maybe even an irreplaceable layer in the verification process? Or do you think technology will eventually evolve to replicate all of these sensory capabilities and dynamic checks, making human inspection totally obsolete?